Hi everyone, I'm Sebastian Brandt, and in this video I will present a lower bound for ruling sets in the local model. This is joint work with Alkida Balliou and Dennis Olivetti from University of Freiburg. So what is a ruling set? An alpha-beta ruling set is a subset of the vertices of a graph such that any two vertices that are in the ruling set have a distance of at least alpha. And any vertex that is not in the ruling set has a distance of at most beta to the closest ruling set vertex. So what we see here is a 2-3 ruling set. A special case of a ruling set is a maximal independent set, which is nothing else than a 2-1 ruling set. And if we look at these two parameters, alpha and beta, one thing we can observe is that if we decrease alpha, then it becomes easier to find such a ruling set, or at least not harder, while the same happens if we increase beta. And two things we can take away from this is that if we want to prove lower bounds, then it suffices to restrict attention to 2 beta ruling sets because they are the easiest ruling sets. And the lower bounds we get will then immediately also apply to the general alpha beta ruling sets. Note that it doesn't make sense to set alpha to 1 because then we can just put every vertex into the ruling set, and that would be a correct ruling set output. The second thing is that an MIS as a 2-1 ruling set is the hardest 2 beta ruling set to compute. Ruling sets have been introduced in the late 80s by Averbuch, Goldberg, Luby, and Plotkin, and since then they have been widely studied in the local model of distributed computing, which will be our model of interest for today. A large part of its interest comes from the fact that it's a generalization of maximal independent sets. And the MIS problem itself is one of the most important and best studied problems in the local model. And ruling sets can also be used for a similar purpose as MIS, which is that of a symmetry breaking subroutine in algorithms for computing solutions to other problems in the local model. Now, what do we know about the complexity of computing such 2 beta ruling sets? On the deterministic side, we know that we can compute an MIS in polylog n time, and here n is the number of vertices of the input graph. And that implies that also for any beta that is at least 2, we can compute a 2 beta ruling set in polylog n time. And this is due to a recent breakthrough result on network decompositions by Roson and Ghaffari. On the lower bound side, we have log star n lower bound for beta at least 2, which goes back to lineal from the 80s. And this lower bound holds up to some beta that is roughly log star n. And for higher beta, we don't even have such a lower bound. So there we don't have any non-constant lower bound. In contrast, if beta equals 1, so if we are in the MIS problem, then we have this log n divided by log n lower bound. And of course, it would be very nice to generalize this lower bound, or the way how this lower bound is proved, to larger beta. But unfortunately, there is a simple reason why this cannot work. And the reason is that this lower bound is first proved for maximal matchings, and then lifted to the MIS problem by arguing that a maximal matching is nothing else than an MIS on line graphs. So the worst case instances for this lower bound are line graphs. And as Kuhn, Mause, and Weidner showed, on line graphs, it's easy to compute a 2 beta ruling set if beta is at least 2. In fact, already computing a 2-2 ruling set can be done in O of log star n time. So if we want to get any lower bound that is better than log star of n, we need a different approach. Another interesting conclusion from the fact that this lower bound has line graphs as its worst case instances is that it doesn't work on trees. So for MIS on trees, we don't have anything better than a log star n lower bound. Now, these are our new deterministic lower bounds, which basically say that there is no sub-polylogarithmic algorithm for 2 beta ruling set. And since the lower bound already holds on trees, we get the first super polylog star lower bound for MIS on trees. Here, the beta in our bounds can be up to some polylogarithmic expression in n. On the randomized side, our lower bounds get exponentially worse. So instead of a polylog n lower bound, we now have a polylog n lower bound. And well, on the upper side, upper bound side, we have this expression for general beta. And I don't want to go too much into detail on this expression. Let me just say that if beta is 1 or constant, then this expression is polylogarithmic in n. And then if we increase beta, then the bound becomes better and better until it becomes polylog log n for some beta in polylog log n itself. So for small beta, our polylog log n lower bound is still exponentially far away from the polylog n upper bound that is given by these works. And especially on trees, we even have a root log n lower bound for MIS due to Gaveri from 2016. So there, the question whether the correct answer is polylog log n or polylog n or something in between is still wide open, while in the deterministic case, we know that the correct answer must be polylogarithmic. We just don't know what the correct exponent is. All right, before I tell you how we prove our lower bounds, let me quickly remark on the model. So we will use the usual local model of distributed computation. Just for the technical parts in this talk, instead of using O of log n bit unique identifiers as would be usual in the local model, we will use O of delta squared and O of delta squared input vertex coloring. But the bounds we get out from the model with a slight tweak can easily be lifted to the proper local model. All right, so one of the main techniques we use in our work is the round elimination technique, which roughly speaking has the following idea. Say we want to prove a lower bound for some problem pi 0. So we want a lower bound on the complexity T0 of this problem. So the idea in round elimination is that we first find another problem pi 1, for which we can show that the complexity of this problem is at least 1 round less than the complexity of this problem. Then we find a problem pi 2 whose complexity is at least 1 round less than the complexity of pi 1, and so on. And if we get to a problem pi k, for which we can show that it can still not be solved in 0 rounds, then we know, since we lost at least 1 round of complexity in each step, that the initial problem pi 0 must have a lower bound of at least k plus 1. And since this technique is used to prove lower bounds, this sequence of problems is called a lower bound sequence. And such lower bound sequences have been used to prove a number of lower bounds for various problems, most of them in the last 2 or 3 years. A dual concept to that of a lower bound sequence is that of an upper bound sequence, where we require that any subsequent problem in this sequence has a complexity that is at most 1 round less than the complexity of the previous problem. And now if we get ever to a problem pi k that we can solve in 0 rounds, since in each step we lost at most 1 round of complexity, we know that the initial problem pi 0 must be solvable in k rounds. And now you may ask, why do I tell you about upper bound sequences when our goal is to prove a lower bound sequence? And the reason is that we get this lower bound by first proving an upper bound and then turning this upper bound into a lower bound. Or more precisely, what we do is we find an upper bound sequence for the problem pi 0, which we'll set to be 2 beta ruling set, which will then give us an upper bound for 2 beta ruling set. And then we will turn this upper bound sequence into a lower bound sequence that will give us our desired lower bound. Okay, so how do we get such an upper bound sequence? One idea would be to take an existing algorithm, and for technical reasons, such an algorithm would be an algorithm that works in our setting where we have an O of delta squared input coloring, and where the complexity of the algorithm can be phrased in terms of the maximum degree delta of the input graph. And then find a way to transform this algorithm into an upper bound sequence. And indeed, there are two very similar algorithms by Schneider, Elkin, and Wattenhofer, and Kuhnmaus and Weidner that give us a complexity of beta times delta to the 2 over beta. So something that is it's a complexity that is phrased in terms of delta in the setting with an O of delta squared input coloring. But unfortunately, it's far from clear for both of them how we would turn those into an upper bound sequence. So what we do instead is we come up with our own algorithm, and then this algorithm will have the property that it can easily be transformed into such an upper bound sequence. Interestingly, the upper bound we will get from our new and genuinely different algorithm will match exactly this asymptotic bound from the other two algorithms. And one main idea in our algorithm construction and in our construction of the upper bound sequence will be to inject some coloring component into this 2 beta ruling set problem. And with that, I mean that we want to find a class of problems such that each problem in this class has both ruling set constraints as well as coloring, vertex coloring constraints. And then we will use the class of problems that we define to build our upper bound sequence from this. We will see how we can profit from having both ruling set and coloring features in the same problem. So here's our problem family. Each problem in the family has beta plus 1 parameters x0 to x beta, and these parameters define a color space. So in this color space, each color has a level from 0 to beta, and the parameter xi will tell us how many colors do we have on level I. And we will assume that all of these colors in the color space are distinct. Now the task of each node will be to output either a color, which will then implicitly also assign a level to the node, or a pointer, which just means I choose one of my neighbors and point to this neighbor, plus explicitly also a level from 0 to beta. Now such an output will be correct if it satisfies the following local constraints. First of all, the nodes that output colors, the colors we get from these nodes should form a proper partial coloring. Okay, so we cannot have any two nodes that are endpoints of the same edge that output both the same color. The second constraint is that if I output a pointer to a neighbor, then this neighbor has to have a strictly lower level than I do. So how is this related to our 2 beta ruling set problem? Let's look at the problem where the first parameter is set to 1 and all the other parameters are set to 0. In this problem, we just have one color, and this color is of level 0. And I claim that if we have a correct solution to this problem, then in 0 rounds of communication in the local model, we can transform this solution into a correct solution to a 2 beta ruling set problem by doing just the following. Each node that outputs a color in the solution to this problem will go into the ruling set, while every node that outputs a pointer and a level will instead not go into the ruling set. Now, the proper partial coloring constraint in this problem will make sure that no two adjacent nodes will output a color because we only have one color. And that will mean that no two neighbors go into the ruling set, which makes sure that our first constraint in the ruling set definition is satisfied. And well, to satisfy the second constraint, we can observe that if I'm a node that points to a neighbor, then to find a close ruling set node, what I can do is I just follow the chains of pointers starting at me. And due to the second constraint, to the second correctness constraint of the problems in our problem family, we know that each time we traverse a pointer, the level drops by at least 1. And even if I start at level beta, after at most beta traversed pointers, I will be at level 0. And at level 0, there are only nodes that output a color because none of them can output a pointer. So I have found a path of length at most beta to ruling set vertex, which means that any vertex has a ruling set vertex in distance at most beta, and also the second constraint in the definition of a ruling set is satisfied. In contrast, if the parameters of a problem, our problem family, add up to theta of delta squared, then it is very easy to solve such a problem in 0 rounds, since we are given an O of delta squared input coloring. We just have every node output one of those colors, and none of the nodes will output a pointer plus a level. So the proper partial coloring constraint will be satisfied because the input coloring given is proper, and the correctness constraint regarding the pointers will be correct because we don't have any node that outputs a pointer. And now we will use these two problems to build the endpoints of our upper bound sequence. So the first problem, pi0, will be our problem that only has one color. And the last problem, pi k, for which we want to show, or for which we need to show that it can be solved in 0 rounds, will be the problem, a suitably chosen problem, where the parameters add up to theta of delta squared. And for the problems in between, well, they will have numbers of colors that gradually shift from one color to theta of delta squared colors. Or seen from an algorithmic perspective, what we want is, starting from a problem that has theta of delta squared colors, we want to reduce the colors in subsequent steps of communication and computation, such that after as few steps as possible, we will get to a problem that only has this one color left. And well, here is how we can perform such a color reduction. Let's say we start with a problem with 8 colors on 3 levels. And the first thing we will do in our color reduction is to group the colors into vertical groups. And then I claim that with just one round of communication and computation in the local model, we can transform this into a correct solution for the problem, our problem class, where only those colors are left that are the bottom colors of our group. And here's how we do that. If I'm a node that outputs a pointer in this problem, then I will just point to the very same node in this right-hand problem. If I'm a node that outputs a color in this problem, what I will do is, in this one round of communication, I will collect the levels and the colors of all my neighbors. And then I will check, do I have a neighbor that is in my group and has a lower level than I do? And if I have such a neighbor, then what I will do is I will uncolor myself. I will become a pointer node. I will keep my level, and I will point to such a neighbor. If I don't have such a neighbor, I will just change to the lowest level color of my group. And the first simple observation is that if we follow these instructions, then the level of a node can never increase. It can only decrease. And this is already enough to show that our color reduction does what we want. So we'll lead to a correct solution to this new problem where we only have the colors left that are the bottom colors of these groups. So more precisely, if we are a vertex that that outputs a pointer in this problem, since I point to the same vertex in this problem by design, and the level of a node does not increase, well, if I pointed to a lower node here, which I must be because here we have a corrected solution, then I also do that in this problem. If I'm a node that has a color but changes to a pointer node, then, well, the node I point to will be a neighbor of mine that has a lower level. So I will point to lower level node, which is correct. And if I'm a node that changes to the lowest level color of my group, then I claim there is no neighbor of mine that can change to the same color. Because if there was such a node, then it must be in the same group as I am. And well, since I don't have a lower level neighbor in the same group, it must be that my neighbor has a higher level than I do. But then I am a lower level same group neighbor for this neighbor of mine. So it will be in this uppercase, and as such, it will uncolor itself and not take on the same color as I do. So we see that these rules make sure that in one round of distributed communication and computation, we get from this problem with 8 colors to this problem with 4 colors. Now, one just has to do the math, how fast we reduce colors with this process. And what we will see is that to get from this initial problem that has delta squared colors roughly to our last problem or our first problem that only has 1 color, we will need theta of beta times delta to the 2 over beta steps. So this will be exactly the same upper bound that we have seen in the other 2 algorithms. Now, to get from this upper bound or this upper bound sequence to a lower bound sequence that will give our desired lower bound, what we will do is we will use a technique that has already been applied in the maximal matching lower bound paper, which is called a wildcard technique. And such a wildcard technique is very useful in the sense that if I already have some sequence given, as we have here with our upper bound sequence, then you just have to compute how many wildcards you need to turn the sequence into a lower bound sequence. Now, this might not be easy, and actually a lot of the technical work has to go into this step, but at least, well, it's relatively clear what you have to do. Now, this wildcard technique loses quite a bit of complexity. So we see that here we have a polynomial and delta dependency, and here we have only exponentially worse logarithmic dependency on delta. But fortunately, this is not the last step. After getting this lower bound that is a function of the maximum degree, we still have to turn this into lower bound that is a function of n, of the number of vertices in the graph. And for this step, fortunately, it doesn't make that much of a difference whether the dependency on delta is linear or polynomial or whether it's logarithmic. Essentially, the difference it will make is whether the bound in n that we get in the end is roughly log n or roughly square root of log n. All right, this is how our lower bound works. I hope you enjoyed the talk, and if you have any questions, let me know.